These are notes for AP Calculus on the topic of limits at infinity and horizontal asymptotes continued. Alright, so here we've got a function that's a piecewise function, and it says find all the horizontal asymptotes for the graph of f. So remember, horizontal asymptotes come directly from your limits at infinity and negative infinity. Here it says show the work that leads to your answer. So you can start with either one. Let's say we start with a limit as x approaches infinity. Well, let's see. There's three pieces to this. Let's see which one would make sense to use. Well, infinity, x is not less than negative 3. It's not between negative 3 and 0, but it is greater than 0. So it makes sense to use the last piece. So on the numerator, we have 2 to the infinity over the negative 1 is negligible compared to the size of 3 to the infinity. So here, notice both of these are exponential. So we're not comparing two different types of functions. However, their bases are different. So let's kind of write out to analyze it. The 2 to the infinite power basically means we've got 3 times 2 forever. And 3 to the infinite power means we have 3, 3, 3, 3. So notice as we keep going, the numerator keeps doubling and the denominator keeps tripling. So because of that, the denominator will eventually get much, much larger than the numerator. So the base is larger. Whenever the denominator is much larger than the numerator, the limit is equal to 0. And whenever you get a specific number like 0 for your answer on a limit as x approaches infinity or negative infinity, that indicates a horizontal asymptote. And the equation of it would be equals this horizontal 0. So there's one horizontal asymptote. Now let's take a look at the other side. We also have to find horizontal asymptotes, have to find a limit as x approaches negative infinity. So for negative infinity, that's not greater than 0, it's not between negative 3 and 0, it is less than negative 3. So we use the top piece, and these are just polynomials. You use the term with the highest exponent that matters. So it would be 2 negative infinity squared right there, and then on the denominator it would be the x squared right here, the highest exponent. Squared. In this case, the negative infinity squared is completely reduced out, and we're just left with 2. And again, another specific number. So we have another horizontal asymptote of y equals 2. All right, the next one, we've got the function f given by f of x is ax squared plus 5 over x squared plus b. And the figure below shows a portion of the graph of f. Which of the following could be the values of a and b? So here's our choices right here. And the key is the two key features on the graph we can see are the asymptotes. So let's take a look at them one at a time. Let's start with our horizontal asymptote, which you can see is y equals 2. And notice it equals 2 as x approaches infinity, this way. So what that tells us is our limit as x approaches infinity of f of x. Notice if it was heading this way with the asymptote, then it would be negative. Here it's positive. So let's see what we do if we would find this limit here. To find the limit as x approaches infinity, you would substitute in the highest exponent, again, the x squared of the numerator. So we'd have ax squared, in this case a infinity squared, over x squared. B is just a constant we're trying to solve for, infinity squared. So notice when we plug in infinity, those reduce out, we just get a. So this limit equals a, but we know the limit has to equal 2, thus a has to equal 2. So if we look at our choices here, a equals 3, nope, that doesn't work. A equals 2, okay, that could work. See, a equals 3, that could work. That can't work, sorry. And a equals 2. So it's down to b and d. So now it's saying, what would be negative 3 or negative 9? All right, let's take a look at our vertical asymptote now. Well, a vertical asymptote comes from something completely different here. It's x equals, this is the equation. X equals, in this case, you can see it's 3. So what this tells us is that when x is 3, remember our vertical asymptotes happen when we get some number divided by 0. In other words, it makes the denominator 0. So if we substitute 3 into our denominator for x, we get 3 squared plus b equals 0. So that would give you 9 plus b equals 0. So b would have to equal negative 9. We subtract the 9 over. So that means our correct answer is D. Another way to see why negative 9 would work is if you put it back in here, you'd have x squared 9, and you can see that would factor into x minus 3 plus 3. Neither of which would cancel out on the numerator here, so they're not going to be wholes. The removable discontinuities, they're going to be non-removable. So you can see there's one at 3 right here, and this one also has one at negative 3. You can't see that part of the graph, but you can see it's starting to look like that over here in the graph. All right, let's take a look at the next one here. So this one combines limits and infinity with our parametric functions. It's moving along a curve in the xy plane, so it's moving in 2 different dimensions. Its position function here is not given to us, they're just told it's x of t and y of t. What we are given is their 2 different derivatives, which are really the velocity. So remember dx dt, this is the horizontal velocity. Telling you how it's moving in the horizontal direction, left to right. And dy dt is the vertical velocity. That tells you how much it's moving up or down, and which way. So describe the behavior of the path of the particle as t increases without bound. So t increases without bound is going to say as t is approaching infinity. Without bound, no boundary, right? It increases, it's going to positive infinity, and with no boundary, it just keeps on going forever. So let's take a look at these one at a time. So let's find the limit as t approaches infinity of dx dt. Well, if we substitute infinity there, we'll have 9 over infinity minus 3. But 9 over infinity, 9 over some huge number, the number is much larger, that's basically 0. So all we're left with then is negative 3 inside there, and it might be easier to analyze if you put this in radical form. That's the cube root. It makes it an odd root of a negative number, so that's okay. It just means the answer is negative. And the key thing here is that the fact that this is less than 0 tells us, this is the horizontal velocity, that we know the particle is moving. Okay. Now let's see what's happening with our vertical velocity. So here if we find out as t approaches infinity of dy dt, substitute infinity e to the negative infinity. And when we have a negative exponent, if we it'll be easier to analyze if we turn into a positive exponent. In this case, move it to the denominator, so that's the same as infinity over e to the infinity. And we've got a polynomial infinity versus an exponential e to the infinity. So this is much larger. And because that's much larger, we end up on the denominator, we end up getting 0. So normally this would tell us if it was positive, the particle is moving up. If it's negative, the particle is moving down. Well, what would this look like? Does that mean it's not moving up or down? Well, kind of. This means that as time approaches infinity, it's approaching 0. But notice, infinity over e to the infinity is not actually exactly 0. It's just really close to 0, right? That's our limit. It's really just a really small positive fraction. So here's what the graph is going to be looking like. We draw it out here. know it's moving left, and we know that the vertical velocity is getting close to zero, so it's not moving very quickly. It's almost not moving at all in the vertical direction. Well, how could that happen? How could it be moving less and less and almost not moving up or down as it moves left? Well, the only way that can happen graphically is if we have some horizontal asymptote somewhere. Could be anywhere. I don't know where that is. And this is positive. I know it's moving up just slightly, not much. So I know it's moving left, so it'd be something like this. So you can see it's moving left, and the vertical velocity, it's almost not moving vertically because it's getting closer and closer to this horizontal asymptote, but never quite touching it. So how we could describe the behavior of the path of the particle, you can say the particle is moving left, and approaching a horizontal. Okay. All right, let's take a look at one more here. So this one is an applied one of these limits in infinity. So it says the total accumulated revenue, the lowest test score exam prep company has received up to time t is modeled by the function r defined below. Okay. And r of t is measured in millions of United States dollars, and t is the time in years since when the company was founded. So we've got a piecewise function, and it says find the limit as t approaches infinity of r of t. Okay, so let's do that first. So the limit as t approaches infinity. Well, t is approaching infinity, so that's not between 0 and 20. It is greater than or equal to 20, so we use the second piece. So it would be 200 squared on the numerator is what's going to matter, over 2 infinity squared on the denominator. Because infinity squareds reduce out. Oops. So then we're just left with 200 divided by 2 is 100. So the limit itself, just mathematically, is equal to 100. That's part of the question. But then it wants us to put this in the context of the problem and explain the meaning of this limit in the context of the problem. And say, um, this means as time progresses, obviously we're not going to an infinite time for this company does not exist infinitely, but as it gets closer to infinity, so you can just say as time progresses, something like that, the total accumulated revenue you can list the whole name of the company, or you just say the company approaches, and notice this is in millions of dollars, so you can write the zeros, or you can just write 100. And that concludes the notes for AP Calculus on the topic of limits at infinity and horizontal asymptotes continue.